Hi everyone and welcome to PrepFusion. So today we'll be starting the lecture 5 for this first chapter, right? Basics of control system. But before that, I gave you homework for few of the questions. We'll solve those. Then we'll start the lecture 5. So in the previous lecture, what did we study? We studied positive feedback systems, negative feedback systems, and what does a positive feedback system do? What does a negative feedback system do? Then we studied sensitivity, right? So before starting the next lecture, we will do this question, right? So what is this question asking us to do is we have to the transfer function is given, right, in terms of m and n, and these are constant. Okay, I hope you understand all this, but if you didn't, I should have mentioned this a bit better, that c1, c2, c3 and c4 are constants. Okay, and this m and n, right, m and n are variables, m and n. Okay, m and n are variables. So now what we'll do is we have to find the sensitivity with respect to this m, right, with respect to this m of the transfer function. Okay, so how will I solve this? Simply write the formula again. I'm doing this slowly, but once you get the gist of it, right, you should do it in a fast manner. Okay, just to explain you guys, I'm doing this very slowly. Okay, so this is delta t upon t by delta m upon m. So delta t upon delta m, what is it? So this is delta t upon delta m times m by t. Okay, times m by t. So what is delta t upon delta m? Delta t upon delta m, again this u by v form, right? So this will be whole squared, and the differentiation of this one multiplied by this one with respect to m. So and the differentiation of this one, that is c2 times this is the whole square, right, multiplied by this one minus the differentiation of the denominator. We don't have a term of m here, so this will be 0 only, so minus 0. Okay, so what do we get? We get c2. Now this one cancel out, right? This one cancels out, so we are left with c3 plus and c4. So this is what the differentiation of the transfer function with respect to ms. Now just put that in the equation, right? Okay, I don't have space. Let me take a new page. Okay, yeah. So now the sensitivity with respect to m will be m by t. What is t? T is c1 m c2 divided by c3 and c4, right, multiplied by this one c2 by c3 plus and c4. So again this one gets cancelled, so what we are left with is sensitivity. This is just a mathematical solution, right? There is no nothing as significance of this, but this type of questions may come in GATE, right? So mc2 c1 plus c2. Okay, so this is the solution for that question, right? Now let us solve another question. So here what they have done is they have simply given all these percentages. Now we have to find these transfer functions c by r. Also we have to find by how much this varies, right? Because just finding c by r normally with this 100 and 4 by 100 will not cut it. We haven't given the variation also, right? Given the variation of the open loop transfer of the open forward path gain, right? Hence we have to find the variation of this transfer function with respect to this variation also. That thing also we have to find. So we need to find two things. One is the normal transfer function, normal closed loop transfer function. Then we have to find the sensitivity. Okay, then only we can write the whole transfer function. Okay, so what I am trying to explain you, I will just solve the question, then you will be able to understand, right? So first what you will do, we'll find the gain without variation, right? First we'll find the gain without variation. Okay, so if you find the gain without variation, then what the transfer function will be? So there is no variation, right? This is 0, so it is g upon 1 plus gh for a negative feedback system. So okay, let me write this: g upon 1 plus gh, which is 100 by 400. So this is 20. Okay, so the value of transfer function is 20. So now let us find the sensitivity of the transfer function with respect to the open loop gain. So like this is like delta t upon delta g by g, but we have already like solved this. What is the result? The result is 1 by 1 plus g. This thing you have to like when you use this multiple times, this will automatically come into your head. But yeah, keep in mind this thing you have to like remember, or you can solve this also, but like this will be helpful in exam, right? If you just know, just in fraction of a second, you know this formula, right? So this is 1. What is 1 plus what is gh? Gh is this, right? 4 only. So 4. So sensitivity is 1 by 5 only. So this is 1 by 5. Now we know del g upon g, right? This is given as 5%, so we can find the del t upon t. Okay, so del t upon t will be equals to del g upon g multiplied by 1 by 5. So this is 5%, so it will be 1%, right? It will be 1%. Okay, 5% by 5 will be 1% only. Okay, so yeah, so yeah, again we can see that this reduces, right? This reduces. Okay, so what is our transfer function with variation, with disturbance? This t transfer function with disturbance equals to, this is 20 plus minus 1%. Okay, so this is our answer for this question, right? C by R will be for this question. Okay, so now we'll move on to like our next lecture. Okay, move on to next lecture, that is lecture 5, and this is like what we'll learn in this lecture is poles and zero, time constant, effect of feedback. All these 3 things we'll learn, and I will give you one homework question. Okay, so firstly, what is poles, right? First what we'll learn like what is poles, after that zeros. Okay, but no, sorry, first we'll learn what is zeros, then we'll learn poles. But firstly let me define like a transfer function. Okay, I have already told you a bit about poles and zeros. Okay, here we'll learn it more thoroughly. So transfer function, how do we write it? We write it as a numerator and denominator, both are functions of s, right? We have one numerator and we have one denominator, both are functions of s, right? So now how are zeros defined? Zeros are defined as these roots of the numerator, right? Roots of the numerator are known as the zeros. Okay, and the roots of denominator are known as the poles, right? Are known as the poles. Okay, so one more definition I can say is where the transfer function becomes 0, where the value of the transfer function becomes 0 for that value of s, like we have a 0, right? That is a 0 of the transfer function. For that value of s for which this transfer function becomes 0, that is a 0 of the transfer function. And what like 0 name suggests itself only. And what do you mean by poles? So for that value of s for which the denominator becomes 0 of the transfer function, or the transfer function goes to infinity, right? The value of the magnitude of transfer function goes to infinity, that value of s is known as the pole of that transfer function. Okay, there will maybe multiple poles and zeros. Okay, that we already know. So let me do one example. Like, let's say we have one transfer function, right? Let me write it here only. We have one transfer function t of s equals to s plus 1 divided by s plus 4. Okay, s plus 1 divided by s plus 4. So we have to find the value of s for which the transfer function goes to 0, or we have to find the root of numerator for us to find the zeros, right? So what I can say is, at s equals to minus 1, this transfer function goes to 0. So transfer function goes to 0, and like poles at the value of s for which this goes to infinity, okay, or the denominator goes to 0. So this is the, sorry for the disturbance outside, this is the poles. Okay, the value of s find the root of this, right? This is s equals to minus 4. So at s equals to minus 4, what happens? This goes to infinity. Like I will write this, expand this further so that you can understand in better manner. So what is this? This is minus 1 plus 1. This is minus 1 plus 4. This is 0 by 3. This becomes 0 only. And what is this? This is minus 4 plus 1. This is minus 4 plus 4. This is minus 3 by 0. Okay, so this goes to minus infinity, like tends to minus infinity. Okay, so this is a pole, right? Like plus infinity or minus infinity, whatever, like magnitude goes to infinity, right? So let me draw the s plane. Okay, I will explain s plane further in like in some lecture, other lecture. Okay, but here what you need to understand, s plane is the, there are two axes, one is the sigma and another is the j omega, right? J omega. So the root of s, right, it may have two component, like the value of s may have two component, either a real component or a imaginary component. So real component will lie in this sigma axis and imaginary component will lie in this j omega axis, right? Okay, what are the meaning of this sigma and j omega? I will explain. So this is a s plane. This is what you need to understand for now. Okay, so like let me put that pole and 0 in this s plane. So this is like the 0, right? This is a 0 at s equals to minus 1. So this is a real value, so it will lie in the sigma axis only. So at s equals to minus 1, just wait 1 second for the disturbance. Okay, sorry for the interruption, actually there was an outside noise. So what I was saying here, yeah, this is not the like the 0, this is the pole, right? So we represent pole like this only, a cross sign. Okay, cross sign. Okay, and a 0 we represent like this, a circle. Okay, we have a 0 at s equals to minus 1, which is also real, like s equals to minus 1, which is also real, so it will lie in the sigma axis. And s equals to minus 4, we have a pole, right? We have a pole, s equals to minus 4. So this is how we basically draw the s plane, sigma j omega plane for a transfer function. Okay, now I will do few more examples. Here what we see, like we have to find the roots, right? They are already in factored form, so I will just write this directly. So what I see, we have a pole at s equals to plus 3, right? Plus 3. If I put 3 here, this goes to 0, hence pole at s equals to plus 3, and we have a pole at s equals to minus 2. Okay, so s equals to minus 2. So this is how we draw like the sigma j omega plane. Now is the system stable or not stable? We'll come to this just after few slides, right? So we have another transfer function. So this is not very simple, right? This is not factored. The numerator is in factored form, but denominator isn't. So what you have to do is find the roots, right? Find the roots. From there we can find the poles. Okay, so what we'll do, find the poles. Okay, what will be the poles? Basically that like that formula, quadratic root formula, right? What is the formula? Minus b under root b square minus 4ac by 2a. Okay, so what is minus b? Minus b is b is minus 2 plus minus b square, which is 4 minus 4 times a is 1 coefficient. So I am not explaining this formula, okay? I hope you can do this. C is 2 divided by 2 times 1 minus 2 plus minus. Now here what we see is this is coming negative, right? This is minus 4 divided by 2. So what we see is like we are getting complex root. Now this part, right? Now the pole has some real component, S has some real component and some imaginary component. So this is minus 1 plus minus j, right? Minus 1 plus minus j. So now this will be interesting to plot in the axis, right? J omega axis. So let me draw the axis first. Sorry for the outside noise actually. This is too much noise nowadays. Okay, this is sigma plus j omega. So what we have is we have the imaginary component as plus minus j1. So I will write here plus minus j, and the real component is negative and it is at minus 1. So it is here only. Okay, so our pole will lie somewhere around here, right? This is the xy coordinate, right? That's how we plot in a graph, right? Xy coordinate. X's real part is minus 1 and imaginary component is plus minus 1. Okay, these are complex conjugate poles, but we didn't find the zeros. So zeros are very simple, right? 0 is at s equals to minus 2 only. Okay, at s equals to minus 2, that whole transfer function goes to 0. So at s equals to minus 2, s equals to minus 2, this whole transfer function goes to 0. So this is figure of S plane with complex conjugate poles. Why is it making this much sound? I don't know. Okay, in the left hand side of the j omega axis, right? This is known as the j omega axis, right? The y axis, j omega axis, and this is known as the sigma axis. Okay, now like what is the importance of poles? Like what do they actually mean? So poles, right, describe the time response of the system. By this, what do I mean? I will explain. Okay, poles, just right these are not, just listen to me what I am saying, right? Poles describe the performance of the system. Poles describe the stability of the system. Poles describe the time constant for a first order system. Okay, for a first order system, they describe the time constant. Also, like for any order system, right, they describe the time constant. Now what do you mean by time constant? We'll come to that. Okay, poles describe the frequency of oscillation for a second order system. Okay, like by what frequency they are oscillating. All this I will come right. Just like listen to me what I am saying. Now poles describe the order of the system. This is very simple only, right? Very simple. Like order means how many number of roots are there in the denominator, right? That's what simply order means. Or order, you can say the number of independent components, like independent energy storing components present in the system. Okay, for RC you can say that, but for other things we can't define RC, right? That's also another definition. Now poles describe the type of the system. By type, like you know how many poles are there at s equals to 0. That is what basically type means. Okay, I will explain also type in next few slides. Okay, just try to know this. If you know this already, then that's good. This is a revision. If you don't know, that's fine. Okay, I will explain it to you in the next few slides. Okay, now like let us understand a stable and an unstable system. Stable system means like after a certain time, right, after like t equals to infinity, the signal is bounded. Okay, for the like the time domain response of the system, right, it should be bounded. It should not be unbounded, that is, it is going to infinity. It should stabilize to some constant value. Okay, or 0, whatever you want to say. Okay, so let me write a stable system, time response of a stable system, right? So let me take an example. X of t equals to e is to power minus 2t u of t. Okay, so in this case, right, what is the value of x at t equals to 0 plus? At t equals to 0 plus, the value of x is 1. And what is the value of x at t equals to infinity? At x equals to infinity, right, it is 0. So the system is stable, right? Why? Because it is settling to some value. It is settling to some value. It is not like changing or oscillatory, or it is not getting unbounded to infinity, right? So if I plot this, right, so much noise, man. Just wait a second, huh? This noise, let this noise go. Yeah, sorry for the disturbance actually. So yeah, this was the signal that I was plotting. So now what I will do is I will plot the sigma plus j omega axis. This is starting from 1 and going to 0. Sigma plus j omega axis. Okay, so what does this represent? Like, I hope if you do the inverse Laplace, you can see that we have a pole at s equals to 2, right? S equals to minus 2. Okay, s equals to minus 2, we have a pole. Through the inverse Laplace, you will find. Okay, so this is the s plane. Okay, so let me take another example of an unstable system, right? Of an unstable system. For an unstable system, let me take x of t equals to e raised to power 2t u of t, right? So at x equals to 0 plus, we have again one value, but at x equals to infinity, right, we don't have any finite value. It is infinity. Okay, like one more thing, like x equals to like 0 plus, right, this is 1 and this is also 1. So that's why, like, for your better understanding, I'm writing this as 1 times 1, and here also at x equals to 0 plus, this is also 1 and this is also 1. So 1 times 1 is 1 only. So x infinity is infinity. Okay, so now let me draw the time response. So time response, right, it's like this only. Okay, this is 1 and it is going to infinity. We don't know, it's unbounded, right? This is a unbounded signal. So unbounded signals are unstable. That is the time response of the system. If it is unbounded, right, then it is unstable signal. Okay, now j omega, right? So where are the poles and zeros? So there isn't any 0, right, but there is a pole at s equals to plus 2, right? At s equals to plus 2, there is a 0. If you do the pole, if you do the inverse Laplace transform, you will understand. Okay, so what we see is pole is lying at the right half plane, right? Pole is lying at the right half plane of the j omega axis. This j omega axis, right, it is lying in the right half plane. So if the poles, right, of the transfer function lying on the right half plane of the j omega axis, then the system will be unstable. Just remember this. If all of the poles lie on the left half plane of the j omega axis, then the system will be stable. Okay, so here, due to this, right, it is unstable. Okay, so here I've like written it down also. All poles lie in the left half of the s plane will be stable, right? If one pole lie in the right hand side of the s plane, that is a j omega axis. I should write this as like j omega axis. Okay, j omega, this you won't be able to understand because yeah, here I don't have that font. So just understand, this I mean by j omega axis. Okay, then system will be unstable if complex conjugate poles lie in the imaginary axis. This complex conjugate poles, right, lie on the imaginary axis, then the system will be marginally stable. By marginally stable, what do I mean? I will explain in the next few slides. Just understand this, that if the poles are purely imaginary, right? If the poles are purely imaginary, that complex conjugate means here in the lies on the imaginary axis, that means the poles are purely imaginary. Here poles are purely imaginary, then the system will be marginally stable. Okay, now if repeated poles lie on the imaginary axis, then the system will be unstable. Okay, if repeated poles lie on the imaginary axis, then the system will be unstable. Okay, so here, like if you have two poles at s equals to minus j2, then the system will be unstable. If we have complex conjugate poles on the imaginary axis, then the system will be marginally stable. What do I mean all this? I will explain. Okay, so yeah, let me first take example. This is the frequency of oscillation. I will explain. This frequency of oscillation, right, is the this component, right? This will be we'll understand much better in the time response chapter. But here, right, this plus j1 minus j1 that we found out, right, here, this, right, plus minus, this is the, like, not the j, frequency of oscillation is a real term. So this plus 1 and minus 1 are the frequency of oscillation, or we can say 1 radian per second is the frequency of oscillation for this transfer function. 1, okay, only 1. Okay, plus minus j is because they are complex conjugate. Okay, that's how we explain the frequency of oscillation. This we will better understand in time response chapter. Okay, so let me first take an example. Let's say we have a frequency of oscillation omega naught equals to 2 radians per second. Radians per second. What do I mean by this? I will also explain to you, right? So this is, now there can be three cases, right? The system can be stable, unstable, or marginally stable. Okay, all of them I will come to. Stable, unstable, and let me write this one. Marginally stable. Okay, so there are three cases. So first I will solve for the marginally stable case, right? Let's say I told you, right, if poles lie on the j omega axis, then system will be marginally stable. Okay, so we have this poles, right, sigma. Now they are lying on the j omega axis. So this is, let's say this is 2 radians, right? So they will lie on the plus minus 2. This is minus 2j, this is plus 2j. So what will be our x of s? Equals to 1 by s plus j2 and s minus j2. Okay, so from this you can convert, right? So what do we get our transfer function as? It is 1 by s square plus 4, right? Okay, wait, just wait for the sound. Plus 4, right? So now how can I write this? What I can do is, we know the formula, right, for this. This is a known formula for us. So this is something like, there is some constant term here, okay, not a term of s, and this is the s square plus a square, right? That is for what formula? I have already taught you that is for sine, right? The inverse of this comes out to be something like sine, but for that the numerator needs to be something else. The numerator needs to be what? It needs to be here omega naught, right? This was s square plus omega naught and omega naught square, and this numerator was omega naught only. So yeah, here what I need to write here is 2 times, okay, not like this, 1 by 2 times divided by s square plus 2 square. Okay, now I will find the Laplace inverse of this. So this is 1 by 2 and this is sine 2t. So here we can see that this is oscillating, right? This is oscillating. How? Let me draw the like plot for this. So this will be the plot, right, for a sine. Don't take it for exact, okay, don't take it for exact, but we can see this doesn't have any steady state value, right? It is oscillating always. That's why we say it as oscillating system, right? Marginally stable. It is neither unstable nor stable, because it is bounded between two values, but it is not settling to any value, right? That's why it is neither stable not unstable, because unstable means it is unbounded, right? It is going to infinity, but it is bounded, right? It is bounded between certain finite values, between this half and minus half. Okay, so yeah, that's why the system is this is x of t, this is marginally stable, bounded between certain values. Okay, so yeah, that's why this is marginally stable. Let's go for the second example, that is the stable system. So for stable system, let me like again take draw the pole zero diagram. The frequency oscillation is 2 only, right? Okay, this is not the pole, sorry, this is not the pole. This is minus 1, right? So now what is the like the frequency of oscillation for this? It is 2 only, and the real component is minus 1. So like what you can do is, like if you solve this, right, if you solve this, there will be some function of x that will be exponential part, and another will be oscillative part. So I am not solving this. If you find the Laplace inverse of this, we'll have some amplitude a, and we'll have some exponential component e to the power minus t due to this real component, right? We'll get this one, and this is homework for you to solve this, right? This is homework for you to solve this. Not everything I will solve. This is sine 2t. This is the oscillatory part. So our system will oscillate like this. Okay, let me draw this. System will oscillate like this. Solve this. Okay, this is homework for you. So what our system will do is, this is sigma g omega, right? This is t, and this is x of t. Okay, so what will happen is, first we'll draw the envelope, right? It will settle to 0 at steady state. This envelope is due to this one at exponential part. Then we'll draw the sine function. Sine function will follow this only. Okay, so it will try to settle to 0. So it is trying to settle to some value, right? It is not going between some value. So this is a stable system. Stable. Okay, so yeah, let's plot the unstable system. We'll do this pretty quickly right now. So what I will do, unstable, right? I will not explain this much. What I will do is simply draw the sigma plus g omega axis. Okay, and this is like unstable, right? So our poles will lie in the right half of the plane. You are understanding, if poles are lying in the left half of the plane, we are getting this stable signal. Now again the same thing only, just that my pole, right, will lie in the right half of this plane. Okay, I didn't draw the poles here, so I should draw the poles also. These are the poles. Okay, so this is +1 only, this is J2, and this is -J2. okay, now how will our signal look like? Again, I will not solve this. I will give homework to this for you. This will be e⁻t and sine 2t times u of t, right? So here also I need to write u of t actually before t less than 0. It doesn't exist. Also the hint is this a, right, will be related to something to this omega naught. Okay, that is the hint. So yeah, this is what I get as the x of t, right? Now what will the signal be look like in plot, right? So yeah, let me again plot this. And this is the envelope, right? So it will become unbounded, right? It will become unbounded. Okay, so signal is becoming unbounded, hence it is unstable. Okay, as we can observe, if the pole lie in the right half of the s plane or the g omega axis, then the poles become unstable. Okay, so yeah, this is it for this. Like we have another question is that, like, this is a very interesting example of Laplace transform, right? This is another example of Laplace transform. So this is the, let's say this is the 16th question, right? We have to plot the value of x of t for this. T raised over e minus t. So this may come in time response or something. So we're doing this into u of t. Okay, so we have to plot this x of t. So how can we plot this? What we know is at t equals to 0, what is the value? Like you may think that, yeah, I may find the value of t equals to 0 at t equals to infinity, then I will use both of them, right? Like just connect both of them, but you can't do that. So x at t equals to 0 plus, what is the value? It is 0 times 1 times 1, so it is 0 only. X at t equals to infinity, what is it? It is infinity times 0, and this is more more dominant than this t, right? If I break exponential, right, we see more terms like 1 minus t square by 2 factorial, all those things, right? All those things come. Okay, so yeah, just keep that in mind. So times 1 only, so this becomes 0 only, because exponential is more dominating. Exponential is more dominating. Exponential is more dominant. Okay, so yeah, this is 0. So can we just connect? No, because this is starting from 0, ending from 0. It can go like this on, it can go like this also, it can go like this, we don't know. So what we need to do is simply plot the three different functions, right, differently, and then multiply those two. Like this one is u of t 1 only, so that doesn't matter, plot these two, right? So what I can do, okay, so this is like e raised over minus t e of t only. Okay, so this is going from +1 to this 0, right? Plus 1 to 0. So okay, and this is, what is this? This is t only. So this is going from 0 to infinity, right? So like what is happening is that if I multiply this two, right, multiply this two, if I multiply these two, what I will get power x of t as is that initially this is decreasing and this is increasing, right? So t much less than t naught, right? Some value, this will dominate. After a certain time, this will dominate. Okay, so the function, how it will look like is, it will increase, then after a certain time it will decrease again. Okay, so here, right, t naught, here the slope will be positive, here the slope will be negative. Okay, and here the slope changes, right? So here the sign of slope changes, so here the slope becomes 0. From positive it goes to negative. So the maximum value, right, simply we just learned in 11-12 that where the slope is 0, it will be maxima, right? Maxima or minima, in this case it will be maxima. Okay, so we can find the value of t naught, and what you can see is what are the poles of the system, right? The poles of the system will lie, there will be repeated poles, and if you solve this in the Laplace domain, there will be repeated poles. Basically I'll solve this anyways. So what is x of s, right? X of s is simply, this is 1 over s plus 1 whole square. Why? Because this is 1 over s square and we're shifting the s by plus 1, so that's why. So what we see is, we have a stable system, right? Stable system, like this is important in the time response chapter, so I'm just explaining it to you now only. This will be come in handy in the time response chapter, right? So this is here we have repeated poles, right? -1 comma -1, repeated poles, negative, equal, real roots. Okay, so this is one thing. So the system is stable because poles lie on the left hand side of the spline. Okay, so yeah, that is it for this question. Like I hope you understand. Like even if like I will give you an example, a few examples, right? I will not solve it because lecture will go very long. Like if, right, we have sigma and j omega, and if the poles, right, if the poles if repeated poles lie here only, then system will be, these are repeated, right? System will be unstable. Sorry for the disturbance, actually like the light went off, so that's why I had to stop the recording again. So as I was explaining, right, if we have repeated poles, then what will happen, we'll get unstable system. Even if it's at the omega axis, we'll get unstable, not marginally stable, if we have repeated poles, right? So one more example I can take here is like of unstable system. Like you do already understand this, but still, this is sigma and this is j omega, right? Now if we have multiple poles here, like on the left hand side of the j omega axis, but we have one pole, only one pole here, then also due to this one pole, right, this will make the system unstable. Okay, this will make the system unstable. Okay, so yeah, due to this one pole also the system will make unstable. Okay, but like if I have complex conjugate poles on the imaginary axis and one pole is the left hand side, then the system will be stable only. then Z will be stable only. Okay, so yeah, all these are examples. Even if there is one pole on the right hand side, right? This, just remember this, even if there's one pole in the right hand side, this will always make the system unstable. Okay, so yeah, this was for the stability and pole zeros. Okay, now what we will study is like one thing, like this is not that important. Okay, if you are able to understand it, good. If you aren't, just skip this part. Okay, this is just for those people who are really into this pole zeros and stuff. Like what I will teach you is how to realize poles and zeros intuitively, right? Realize and zeros. So like me and Himanshu both have us have done a video on YouTube. You can see that video also. I will just explain in brief here, right? Explain in brief. Intuitive, right? So what will this be? So this is, let's say we have one circuit, right? CR circuit. We know this is a high pass filter. If you don't understand what is high pass filter, don't worry. This is a high pass filter, and we have to find the transfer function, poles and zeros of this for the voltage transfer function, right? V over Vs, we have to find the poles and zeros. So how can we find this intuitively? So let me first break this down into some series combination of impedances, right? Series combination of impedances. So this is Z1, this is Z2, and this is VO, this is VI. Okay, so this is just a voltage divider circuit, right? So our VO, right? VO will be VI times Z2 divided by Z1 plus Z2. Okay, VO will be this one. Okay, so V over Vi equals to Z2 divided by Z1 plus Z2. This is a transfer function, right? This is a transfer function. Now, how to find the zeros? If this transfer function goes to 0, so how can it go to 0? Either this Z2 goes to 0, if Z2 equals to 0 and Z1 is not equal to 0. Why? Because if both of them becomes equals to 0, then we will have a 0 by 0 format and it will be undefined. So if Z2 goes to 0, then this transfer function will go to 0. If Z2 goes to 0, that means this is short circuit. Okay, this is short circuit. And if Z1, right, Z1 goes to infinity and Z2 is some finite value, then this transfer function will again go to 0, because in the denominator we have infinity and in the numerator we have finite value, so it will go to 0 again. So if we break the link or if we short the output, then we will get a 0. Okay, two conditions. And for poles, right, for pole, what you need to do is this, right, this denominator needs to go to 0. Okay, so this Z1 plus Z2 needs to go to 0, then we will get a pole. Or one thing is that you can see infinite impedance from here. If you don't understand this infinite impedance, like shorting this, make this independence so 0, don't worry, no need to like think that much. Okay, just make this Z1 plus Z2 equals to 0, then we'll get a pole. So for 0, right, 0, what we need to do? We need to make Z2 equals to 0. Z2 equals 0 for that value of particular frequency, then we will have a 0, and Z1 should not be equals to 0. So this is short the output. This is short the output, or Z1 equals to tending to infinity. Okay, and Z2 is finite, right? This is break the link between input and output, because this is getting infinity, so the input and output are unlinked. Okay, so and for poles, right, for poles, Z1 plus Z2 equals 0. So Z1 equals to minus Z2. Z1 equals to minus Z2. So this is basically for poles. Now what I can say is, can I break the link? Can I break the link here? Can I short the output? No, because this R is constant. It doesn't change with frequency. I can't short the output. Can I break the link? Yes. At DC frequency, at s equals to 0, at s equals to 0, this, right, this is going to infinity. 1 by cs, s equals to 0, going to infinity. So we can break the link, right? So break the link, okay. And like for poles, right, for poles what we will do, just simply make that 0, right? Impedance 1 by sp c plus r should be equals to 0, right? So sp equals to minus 1 over rc. We can see it is on the left up plane, okay. Now what is the like time constant is the negative inverse of this pole, right? This will come in the next slide. I'm just writing the time constant for now, don't worry, okay. It is the negative inverse of this. So I hope like Himanshu also taught you this, okay. So now one issue is that I won't be able to find the like the low frequency gain for this. The whole transfer function I won't be able to find, because at s equals to 0, right, we get 0. So the DC gain I won't be able to like write. DC gain is 0 only. So we have the transfer function, we write it like this only: a into the zeros divided by the poles, numerator by divided, right? This is a constant value, okay. So numerator is what we have, a 0 at s equals to 0. So s equals to 0 is 0, and 1 plus s tau. I will just explain you the standard form just in the next few slides. 1 plus s tau. So tau is rc only, so src, okay. But what is the problem here is, we don't know at s equals to 0 this transformation goes to 0, right? So we have to find the for this, to find the value of a, right, there will be some constant in this in front of the transfer function. So to find this value of a, we need to go to the high frequency response. If you don't understand, I have explained this more thoroughly in the in my realizing poles and zeros video, or you can watch Himanshu's video, okay. Both of these videos you can watch. Else like I have to go fast here, because this is not that important to gate, but still a few people may want to know this, right? So yeah, this is that. Now we have to find the high frequency again. We have to find the high frequency again, right? So to find the high frequency again, what we can do is simply put s equals to infinity, then the circuit becomes something like this. This is shorted, this is r, this is VO, this is VI. So VO equals to VI. So high frequency gain is 1. So this A, what does high frequency mean? We only take the coefficient of the s terms, right? For high frequency, limit s tends to infinity, take the coefficient of s, okay. I hope you have studied limits and all those things, okay. So yeah, this is A, on the numerator will be remained with A, denominator will be remained with RC. This is equals to 1. So A equals to RC, okay. A equals to RC. So what do we get our transfer function as is VO over VI of S equals to SRC by 1 plus SRC, okay. This is our transfer function. So yeah, this is basically one method like to solve for poles and zeros intuitively, okay. Like this is not that like not that important. If you didn't understand, that's fine. If you did, that's great, okay. Now let's go and solve the concept of time constant, okay. So what does time constant mean? Look here, I will explain you what does time constant mean. Time constant is defined as the reciprocal of magnitude of negative real roots for a stable system, okay. Time constant is defined as a reciprocal of magnitude of negative real roots of a system, okay. So for a stable system, time constant is defined only for stable system. So the real part, right, S has imaginary real part, so the inverse of the real part is known as the time constant for a stable system. Time constant, there can be many time constant in a system, right, because like there can be many poles. So each pole has its real component, and that inverse, negative inverse of that real component is the time constant, or the magnitude, you can say, magnitude you can say, okay. So let's say I have one signal x of s equals to 100 by s plus 4, right? So now what will be the time constant for this? Simply I have to find the roots. So first what I will do, draw the sigma plus j omega axis. Okay, this is not okay. Okay, this is bad. something is happening. Sigma plus j omega axis. So this is minus 4, right? So time constant will be what? Time constant will be negative inverse of this. So magnitude of the negative inverse is 1 by 4 seconds. Okay, time constant is 1 by 4 seconds. Now, like, what this in Laplace domain, right? What is this behaving as? This is behaving as like a low pass filter. Why? Like low pass filter, what it does? It passes the low frequency signals, but it blocks the high frequency signals. So if I put s equals to infinity, high frequency, then this transfer function gain becomes 0. If I put s equals to 0, we have finite gain. So the response will be something like this, right? So it passes the high frequency, low frequency signals, and it blocks the high frequency signals. So this is like a this time constant, right? We can also say that this finds the bandwidth for a first order system. How? The inverse of this time constant, right, will be the bandwidth of the first order system. So these are terms to note, right? Terms to note. Okay, this is value held for first order system. Okay, so for a first order system, this is valid. So what is this? One over time constant is 1 over 1 over 4, it is 4 radian per second. Okay, 4 radian per second. Okay, so yeah, this also we can say, right? This also we can say. Okay, or what you can do, you can convert, right? For a standard first order circuit, you can convert this term, right? This okay, let me this term with e raised to power minus t upon tau, e raised to power minus for finding the time constant. Compare with standard term okay. So what is this? So it is e raised to power minus t upon tau. So here, right, if I solve for this transfer function, right, in the time domain, what do I get? So x of t equals to 100 e raised to power minus 40, or not 100, actually I have to take 4 common here. Oh no, this is 100. Yeah, this is 100 e raised to power minus 40. So like comparing this, right, comparing this with this term, so what is the time constant? So comparing this with this, I find that the time constant is 1 by 4 seconds. Okay, time constant is 1 by 4 seconds. Okay, so yeah, this is one very important part. Also we may have more poles, right? More poles, and we'll get more exponential terms. We'll compare those with this standard form, right? From there you can find the time constant. I will just take another example. Okay, let's say I have one transfer function which has like s plus 1 into s plus 2, whatever you want to say. Okay, so what I will get, find the time constants. Okay, like I want to know is what is the time constants. Okay, so how to find those? Basically the roots, right? We can do like this. Roots are, one is minus 1, one is minus 2. So it will, time constant will be negative inverse of this, so it is 1. Second time constant will be negative inverse of this also. Okay, this is 1 by 2. Okay, so these are the time constant. So if I solve this, right, I will get 2 exponential terms. If I solve this with partial fractions, I will get 2 exponential terms. Now compare those with e raised to power minus t upon tau. You will get the time constant as like this only. Time constant like this only. Okay, so like that also you can find the time constant. Now let me take another example. If I have a transfer function xs equals to s minus 2. Now what is the time constant for this? time constant for this. So the time constant, right, the time constant, it will be it does not exist here, okay, because this is an unstable system and time constant does not exist for a unstable system. So pole, right, the pole is lying on the right half of the S-plane or the j omega axis. So the right half of the S-plane, right, so unstable. So time constant does not exist, okay, time constant does not exist for a unstable system. This thing you have to keep in your head, right, unstable system, time constant does not exist. Time constant only exists for a absolutely stable system, okay. So yeah, so now I will write the general time constant form of a control system or a transfer function, right, of a transfer function. So of a control system, I mean, okay, general time constant form of a control system, okay. So what is the like the g of s, what is the g of s? So what is the g of s? G of s I can write here is, we have some gain k, okay, that k I wrote in that form, right. This is a general time constant form into 1 plus, this is just a form and just a terminology, don't need to get into too much of these details, s tau 1 dash 1 plus s tau 2 dash and so on, right. How many number of poles are there, or like how many number of zeros are there, it will go on till that, and we have 1 plus s tau 1 into 1 plus s tau 2 and so on, okay, how many number of poles we have. So the time constant, right, time constants are of this control system are tau 1, tau 2, tau 3 and so on, right, how many number of poles are there, okay. So time constant, like these things you have to keep in mind, time constant does not exist for marginally stable system, it only exists for absolutely stable system, okay. So yeah, so one thing I want to explain to you is that the settling time and relate the speed of the system, right, speed of the system, performance of the system with respect to time constant. Here we'll like understand all those points that I wrote previously, right, about the poles is also related with time constant, right. So about the poles that I told you, all those things we will relate here. So let us have a signal that x of t equals to e raised to power minus t upon tau, right. So how can I write this? So here we have t and we have this as x of t, right, this is e raised to power minus t upon tau, okay. So we can plot this, right, we can plot this. So this is like this only, this is like this only. So this is, what is this value, this is starting from 1 going to 0, okay, and here somewhere we have 4 tau, right. So I hope Himanshu has explained you what is this 4 tau. 4 tau means it settles to like 2% of its final value, like within 2%, like sorry, the error band is 2%, right, it settles to 98% of its final value for 4 tau, right. That is, let's say if the final value was supposed to it was supposed to reach 100, it will reach 98, right, to reach 98 at 4 tau time, okay, that was this 4 tau mean. So 4 tau is also known as t settling time. Settling time has many definitions, but what we'll be mainly concerned with in this lecture, right, is 98% settling time, that is the value of the signal settles to 98% of the final value, okay. So I mean the error band is 2% only, the like how much more it needs to get to reach to the final value is 2% only, error band 2% error band, 98% means 2% error band is left to reach to final value, okay. So t settling equals to 4 tau, right, t settling equals to 4 tau, okay. So it is the time required, like now what does this t settling also mean? It is the time required, like transient anyways, what does it mean? Transient means time required to reach from one steady state to another steady state. Here it was at a steady state, here it is another steady state. Time required, okay? That's what basically speed or settling time means. Now the faster, right, the faster it reaches to a steady state, we'll say, yeah, it is more like high speed, right, more speed, because it reaches a steady state at a faster rate. So speed, right, if the t settling is high, the speed will be lower, it will take more time to reach to a steady state. So speed, right, will be inversely proportional to the t settling, right? If the settling time is lower, it will take less time to reach to a steady state, right? So the speed will be very high, it will reach steady state very fast, okay? That's why it is inversely proportional to t settling. Now we can write this, right, relation as like t settling is directly proportional to time constant only. So speed, right, is inversely proportional to time constant, okay? Speed is inversely proportional to time constant. So like now we can compare three values and we can compare the speeds and the time constant, okay? So let me plot a graph here. This is time and this is the speed, right? This is the, let's say this is x of t only. We have three signals, right? We have three signals. This is one, this is another, this is another, okay? So this is A, this is B, and this is C, right? ABC, okay? So what do you observe is, like, this is reaching its steady state much faster, this is reaching its steady state a bit slower, and this is reaching its steady state much later. So what will happen? The speed of C, right, the speed of C will be higher than the speed of B, and it will be higher than the speed of A, okay? So all these things will be higher. So this is faster response, and this is slower response. This is how you can, from graphically you can understand if a like a system is faster or slower from graphically, okay? So these things that I wrote in point, right, this was one of the points that explain that point, right, about speed and time constant. Poles are related with time constant and time constant is related with speed and it is related with performance, okay? All these things you can relate now, okay? So now what we will do is study the effect of feedback. What happens if we give feedback, and what happens, like initially we don't have feedback, but what happens after giving feedback, right? So system with feedback, let's say we have one system, right, the transfer function is given, gain of the system. So let me draw the pole 0 diagram, that is the S plane, right? So we have one pole at the left half of the S plane, okay? So what is the time constant for this? It is 1/2. I will write down directly, okay? What is the bandwidth for this? First order, right? First order is 2 only, 2 radian per second, okay? I will directly write this now, okay? Now what I will do is find the, like the draw the pole 0 diagram for this one, right? But first I have to write the transfer function. So what will be the transfer function for this system with negative feedback? T of S will be G upon 1 plus GH, okay? This is 1/5 into S plus 2, right? So this becomes 1 divided by S plus 7. What happens? The pole shifts more left, right? Pole shifts more left, okay? Now the pole is at -7, right? Pole is at -7. Okay, pole is at -7 only. So what happens? Pole goes more towards left, so system becomes more stable. And what is the time constant now? Time constant is 1/7. Bandwidth is 7. So what happens? The time constant reduces. So what happens? Time constant, right? Tau reduces, speed increases, and the bandwidth also, like this happens, speed increases, also the bandwidth also increases, which is good. Now it will pass broader range of signals. Okay, so yeah, all these things happen for a closed loop. So I should write this here like a feedback system, right? Closed system. This will differentiate it better. Okay, this is not 7 radians, this is 7 radians per second. Okay, so yeah, this is what is happening. So what is the effect of negative feedback? What is the effect of negative feedback? Is that it reduces the time constant, that is the time required to reach to steady state, right? It reduces time constant reduces. And what happens? Settling time, right? Settling time reduces. Okay, and then what happens? This bandwidth, right, increases. Okay, the speed increases, it reaches steady state much faster. Speed increases, and the pole shifts more towards the left hand side of the S plane. Earlier it was at -2, now it went to -7. So it makes the system more stable. Stability increases. Stability increases, right? So like I'll do a few examples of a negative feedback system. So if you have one signal and we see that it makes the signal bounded, right? It makes the signal bounded, it makes the unbounded signal bounded. So the poles of the signal, one is at 0 and one is at -2, right? So if I use a negative feedback system, it will shift the poles more towards left. Okay, that is what the main thing is if we have open loop transformation like this. Okay, now for a negative feedback system, like this is what I meant by energy regeneration. What does this mean? Basically okay, let me write this a bit better manner. This is energy regeneration. Okay, energy regeneration. So like basically what happens is, sorry, not degeneration, sorry for this, that was for positive. So it takes the energy, right? It makes it to 0. It is going to a 0. So we don't give any energy to this signal, we reduce the energy to this signal. If we have a sine signal, right, we reduce it. It has some energy, right, oscillating, but we reduce it to 0. That's why this is known as energy degeneration. Now what we'll study is system with positive feedback. So again writing the transfer function. This time what will happen is that the transfer function will be g of s upon 1 minus g of s into h of s. So like I will write this directly right now. What is this? This is s minus 3 only. Okay, s minus 3. Okay, you solve this, you will get this. So let me draw the pole 0 diagram. This is simply +3, right? This is simply plus 3 sigma j omega, sigma j omega. So this is unstable, right? This system is unstable. So it was earlier stable, it was at here -2, now it became unstable. So what does positive feedback do? Positive feedback reduces the stability of the system. Positive feedback reduces the stability of the system, right? So also what else, like the poles, right? The poles shift to the right hand side of the S plane. S plane, okay. So this is the effect of positive feedback. So like what will a positive feedback do? It will take a stable signal and it will make it an unstable signal like this, okay. So like this was for that response only, like here, right? This one, right? So transfer function was this only, but it made it more unstable, okay, made it more unstable. And here it made it like it was stable signal only, like the main open loop, right, output, but it made the signal unbounded, that transfer function, right, that response, okay, made it unbounded, okay, made it unbounded. So yeah, this is what a positive feedback basically does, okay. So now like also what this does is, again we have a sinusoid signal, we feed it, what it does is it regenerates, right? It gives it more energy, so the signal amplitude increases further, so it gives this further energy, positive feedback. So there is energy regeneration, okay. Sorry, actually call came up. So what we'll do is we'll do energy regeneration, right? So this is known as energy regeneration, that energy is regenerating. So just these are basic things, like I'm just plotting the response, right? Feedback response, what you are getting here. Also I'm what I did was just plot the response, right? Plot the response of this this thing, okay. This is actually not the response. The actual response is like this one only. We have one e raised to 1 minus 40 70, right? This time 70. What will happen is this time, right, it will settle to much faster rate. So this is wrong, this was wrong previously drawn, okay, did it wrong. This will settle to much faster rate, okay, much faster, speed will become much faster. So yeah, this was the negative feedback response, this was the positive feedback response. Makes the signal unbounded. For a bounded signal, it makes the signal unbounded, okay. So yeah, that's what we studied. Now we will study the initial value theorem, okay. What is initial value theorem? It is used for determining the initial value of a time domain signal directly from the transform domain, okay, transform domain. So this is like what is the definition? Like in the transform domain we can find the initial value of a signal for the time domain value, okay. So let's say we have one signal x of t which has a Laplace transform of x of s, right? Now the limit t tends to 0, that is the initial value 0 plus of x of t. What will be the initial value? It will be x of 0 plus only, right? X of 0 plus only, which will be equals to limit s tending to infinity s times x of s, okay. So from the Laplace domain, right, we can find the information about the initial value of the time domain signal, okay, time domain signal. So this is also another important property of initial value theorem. Now let us do a few examples and there we'll understand, okay. I think this is the 17th question, I don't remember, okay. So the 17th question, right, this is s plus 100 by s plus 4, 100 by s plus 4, okay. So what is this x of 0? What is this x of 0? So either what I can do, either find the time domain expression and from there I can find the initial value, or what I can do here is directly do limit s tending to infinity 100 s times s plus 4. Now I hope you know when limit is infinity here, we only consider the coefficients of s, right? The coefficient of s is 100 here and it is 1 here, so it comes out to be 100 only. Comes out to be 100. Okay, 100 by 1, 100 only. So initial value I can directly find out from here, or what I can do is plot it, right? X of t equals to, it goes from 100 and it goes to 0, right? Goes from 100, like this is the time domain expression. Time domain expression is e raised to power minus yeah, this is the time domain expression, e raised to power minus 40, right? E raised to power minus 40. So like this also you can find the initial value. Here you put the value of x of 0 and you will get that we are getting 100, right? So from this also you can do, but like that is much more better approach. When finding the time domain expression is difficult, finding the Laplace inverse is difficult, you can directly get the initial value from Laplace domain only. So for initial value, right, we'll have three cases. What are the three cases? If order of the numerator, right, if order of the numerator, that is the number of zeros, is greater than the number of poles, right? Number of zeros is greater than the number of poles. Okay, poles. Okay, number of zeros is greater than number of poles, then this x of 0 will be infinity. Why? Because we have like the s term is more in the numerator, right? So it will tend to infinity. I hope you understand. If you have one more s term here, so this s and s will cancel, but this s will remain, so it will tend to give it it will tend to take the signal to infinity, right? That's why the initial value will be infinity. Like I hope you understand basic limits. Okay, so this is if order of numerator of s is less than order of denominator of s, then what will happen? Then x of 0, right, will be 0. Why? Because we'll have more s terms here, so it will tend to go to 0. Now one thing we have to understand is that we have to multiply s here also. Like this order is already plus 1 here. This order is all because we are multiplying with s also. So these things we have to keep in mind that okay, what I should do is, let me write this like this only, that s time g of s equals to n of s by d of s. Why I am writing like this? Because we have one s on the numerator also, extra s, right? That wasn't there previously, g of s. So that's why I'm defining this numerator denominator like this only. We have one extra 0. So then this all of this will be valid, right? So now if, right, order of, that is the number of poles and zeros are equal for this transfer function, right? For this one, s times g of s, for this one, right, number of poles and zeros are equal. Then right, this x of 0 equals to finite, like just like here, right? Here like this poles and 0 not equal, but if I multiply this s, then they become equal, number of poles and zeros for s g of s, right? S g of s. So here they are equal, finite, then we'll get some finite initial value. That is what exactly is written here. Okay. So now, is this initial value theorem applicable, valid for unstable system? Let us do one example. Let us do another 18 problem. Okay, so we have 100 by s minus 4. Okay, 100 by s minus 4. So what will be x of 0 this time? The x of 0 will be limit s tends to infinity s times, this is the, okay, let me write this as x of s actually, else very confusing. So now again we'll just take the coefficients of s terms, right? So this is 100 by 1, this is 100, this is 100. So we are getting initial value, but this system is unstable, so we can find the initial value for an unstable system. That is fine. Why? Because we're just finding the initial value, right? We're not finding the final value. Final value is unbounded, it is infinity, we don't know. But initial value, there will be some initial value of that signal, right? So starting from 100 and it is going to infinity, right? It's going to infinity. Okay, so what is the value of the signal? It is sorry, not 100, it's over 40, it's over 40. Okay, so yeah, this is what our x of t is. Now like we'll take another example of a marginally stable system. Okay, marginally stable system. Equals to 100 by a square plus 25. So how can I write this? So the poles, right? The poles will be on the imaginary axis, so that's why this is like conjugate of imaginary axis, so that's why this is j5 and this is minus j5. Okay, this is a marginally stable system. Now again I will find the initial value, x of 0 limit as s tends to infinity, s x of s equals to 100s upon s square plus 25. Now what do we see? The number of poles is more than the number of zeros, so where it will tend to 0. So okay, I should write this as limit s tends to infinity. Yeah, here I have wrote it down here. Okay, but here also I have written, fine. It will go to 0, right? So initial value is 0. So if I plot this, right, if I plot this, what I can say is this is a sine signal, right? This is a sine signal, it will start from 0 only. This is a sine signal, it will start from 0 only. Okay, and revolve like will be bounded around certain range. Okay, bounded in a certain range. So yeah, it is starting from 0 only. So for marginally stable system also, it is not a problem for find like using the initial value theorem. So yeah, initial value theorem is valid for all stable as well as unstable as well as marginally stable system. Okay, it is valid for all types of system. Okay, so yeah, that is one important thing to note here is now we'll study the final value theorem. Okay, so what is the final value theorem? So final value theorem is used for determining the final value of a time domain signal directly from the Laplace transfer domain. Okay, directly from the Laplace transform domain. So this is also very helpful. Without finding the time domain expression, we can directly find the final value of a signal directly from the Laplace domain. Okay, x of t. If x of t has a Laplace transform of x of s, then limit t tending to infinity x of t, it will be equals to x of infinity only will be equals to limit s tending to 0 s x of s. Okay, this is the final value theorem definition. Okay, final value theorem definition. Now let us take another example. Again, simply take the same example, right? 19. If previously it was 18, right? Okay, no, this one's 19, so this will be 20. This is 20. So x of s, again the same example, equals to 100 by s plus 4, right? S plus 4. So what will be your x of infinity? x of infinity equals to s tends to 0 s times 100 divided by s plus 4. Now put s equals to 0 on both numerator and denominator. What do you get? We get simply 0, right? It's simply 0. Okay, so we know we have already plotted this pose 0. I will not plot this. This is a stable system. And we are getting a finite final value, right? We're getting a final value. So what is the again the time domain expression? I've already drawn it, but still I'm again drawing it. From here also you can see that yes, it is settling to x equal to 0, right? This is going from 100 to 0. Okay, so this is photo, right? This photo. Okay, so yeah, this was for this domain. Now let us do another example. This is this was 20, so let us do this 21. So this time, right, the x of s equals to 100 by s minus 4. Now pole is lying on the right up plane, so we have to find the x of infinity. So again, if I apply the final value theorem, what I will get is simply limit s tends to 0 100 times s divided by s plus s minus 4, right? So what if I put s equals to 0 here? I get 0. Okay, I get 0. So this is this correct? No, like as I plotted the signal earlier, right, it was unbounded, it was going to infinity. So this is incorrect, right? This is wrong. This system is unstable, hence not valid for unstable signals, right? Not valid for unstable signals. Okay, so yeah, this is one thing to keep in mind, is that it is not valid for unstable signals. So now what I will do is write the like again draw the time domain expression. I've already drawn it, but still to like keep everything in sync, draw the time domain expression. This is t starting from 100 and it is going to unbounded, right? So here we can see this is unbounded. So final value theorem is not applicable for unstable system. Final value is infinity for in this case. Also for like marginally stable, right? Marginally stable, the same thing will happen again. X of s equals to plus 25. X of infinity equals to what? So x of infinity limit as s tending to 0 100 s by s square plus 25. So where does it go? It goes to 0 times 100 divided by 0 plus 25. So it is going to 0 only, but is it really? No, it's a sinusoid signal, right? Sinusoid signal, so it doesn't settle to any value. It doesn't have any final value, because we don't know what is the final value, right? It is revolving within certain range, right? Okay, revolving within certain range, so it doesn't have any final value. So for marginally systems also, marginally stable system also, this final value theorem is not applicable. Okay, so yeah, that was the expression. So let me write the few key points. Key points is final value theorem is only valid for absolutely stable system. Final value theorem is not valid for unstable or marginally stable system. Okay, so yeah, that is one thing, and this is one homework question I will give you. Okay, this lecture has already gone very long. Take the screenshot, and in the next lecture I will revise you the concepts, and we'll do this question. Okay, and we'll start few other topics like the dominant pole concept and other concepts. Okay, thank you for watching.